Afternoon everybody, welcome to the second lecture on connected particles. So in this lecture we're going to be looking at something called force coupling and also objects in contact. First of all, if you want to access any of the resources from this lecture, if you're a Bilborough College student, you can get them from parkermaths.com/year1maths. If you're watching from anywhere else, you can access them from parkermaths.com/remote learning, and all the PowerPoints should be on there for you to load up. So one other thing before we start, particularly if you're loading this on a mobile device, YouTube may have altered the quality, the default quality. So if you find you're having difficulty reading anything, you might want to go to the setting down here. If it doesn't say HD, change the quality to something higher so that you can see the writing. If you're viewing it on a normal computer, you shouldn't have that issue though. Okay, so let's get started with some connected particles then. So last lesson we looked at pulleys, and we're going to start with objects in contact this time. So a quick reminder of what we looked at last time. We said Newton's third law was that if object A exerts a force on object B, then object B exerts a force of equal magnitude but in the opposite direction to A. We had a look at that diagram last time. Okay, so what I'd like to do to start with, you've hopefully met the normal contact or normal reaction force before. What I would like you to do is have a go at just part A on here. It doesn't matter if you get it wrong. Most people will get one of these three parts wrong the first time that they try them. Okay, but you'll hopefully learn from your mistakes if you do that. So we've got Bill standing on a lift platform, and he's got a mass of 82 kilograms, and the lift platform has a mass of 125 kilograms, and it's suspended by this cable here, and it's accelerating upwards at 0.4 meters per second squared. And I want you to draw three separate force diagrams for it. The first one is for the forces acting on Bill. The second one for the forces acting on Bill and the lift at the same time. And the third one, just the forces acting on the lift. So I've got an outline of what it could look like here. You've got Bill and the lift, and the lift. Just add the forces on how you think they will work. I'll give you a couple of minutes to do that, and then I'll show you my answers and talk through why I've got them set out as they are. Okay, so with Bill, we've got two forces that are acting on him. We've got the weight going downwards and the normal reaction force from the floor acting onto Bill, which we call R. And we've got an acceleration upwards of 0.4 meters per second squared. I've just been told that a few people are having difficulty loading this PowerPoint up. what I'll do, I'll email it out to everybody at Bilborough College in a few minutes when I've gone through this example. But for the time being, hopefully you'll be able to just watch what's going on the screen, and that'll be enough. Okay, for Bill and the lift combined, the lift has a mass of 125 and Bill has a mass of 82. So we need to add those together if we want the total mass first of all. And then we're going to have, that is going to be our mg force. 82 plus 125 is 207 g. And we've got a tension holding the lift in place up here. Now the third one is generally where people start to go wrong. So the forces acting on the lift are as follows. Okay, most people are okay with the tension force up here, but they don't get this bit right here, the R plus 125G. So I just want to have a think about why that is. Okay, so if you imagine that Bill is standing on the lift platform, and in the first diagram we had the forces acting on Bill, there was a normal contact force acting upwards onto Bill. That means by Newton's third law, acting on the lift, there must be a normal contact force acting downwards. That's where the R bit comes from. But the lift platform itself already has a weight, and that weight is 125 G. And so the total force acting downwards is R plus 125 G. Now this R here is not, in this case, going to be equal to 82 G. If there was no acceleration, then that would be the case, but because it's accelerating upwards, that won't be the case. So this diagram is the more tricky one to work out. Now fortunately, there aren't that many circumstances where you actually need this diagram. The most common one you would use are these two here, generally because you'll only have one unknown in each of these, and you'll have two unknowns in this one. But it does illustrate a more general point here, and that is that if there's a normal contact force acting upwards on one particle, then there'll be a normal contact force in the opposite direction that's the same magnitude on the other particle. Okay, so let's just go back and have a look at part B there. We're going to calculate the normal reaction force which acts on Bill. So when you come across a problem like this, you need to just decide which diagram you're going to use. If you're not sure, you may have to draw all of them out, like this. Now if we want to calculate R, the normal contact force, and we look at these three diagrams, there's only one logical choice, and that is the forces acting on B, because this is the only diagram where R is the only unknown. Bill and the lift doesn't have R, and the lift on its own has T missing as well, so we can't use that. So in this question, we're going to use the diagram for Bill on his own. So that's what we've got here. Then all we need to do is resolve vertically. So we'll take upwards to be the positive direction, and we'll have R minus 82G. So net force is the forces up, which is R, minus the forces in the opposite direction, 82G, and that equals mass times acceleration. So that's going to be 82 times 0.4. Okay, so we could rearrange this in our head. We're going to do 82 times 0.4, and then if we move that to the other side, we'll be doing plus 82G. If you put that into your calculator, you get 840 newtons if you do it to 2 sig fig. So what I neglected to say there was G I'm using as 9.8 in these questions, so I've given my answer to 2 significant figures. In part C, we're calculating the tension in the rope, which is raising both Bill and the lift platform. Going back to our diagram, there's actually two possibilities we could use now. We can use diagram 2 here, Bill and the lift combined, because that only has T as the unknown. But now that we know R, if we wanted to, we could also use the diagram with the lift, and we could do the R that we just found plus 125G. In this case though, I'm going to use this value here. So we've got our diagram on the left hand side. Again, we're going to resolve upwards. So the forces we've got going upwards are T, and the force downwards 207G. So we get 2T minus 207G. And that equals mass times acceleration. So the total mass here is 207, and we multiply that by 0.4. Again, we're going to do 207 times 0.4, but then we'll move this term over to the other side and add 207G. And if you put that into your calculator, you get 2,100 newtons to 2 significant figures. Okay, so the calculations involved in these kind of questions are incredibly simple in terms of writing down the force equations. The tricky part is, in some situations, there's more than one diagram that you could draw and use, and so you need to figure out which diagram is most appropriate. As you get more experience, you'll kind of just start to do that intuitively, but to start with, if necessary, you might have to draw more than one force diagram first, and then you can go, oh yeah, this is the one that I need. Okay, so I've got a problem that's similar for you to have a go at for yourself now. Okay, and they're all in the PowerPoint, starting on slide 41. There's a few similar questions to the one I've just done. What I'm going to do, I'm going to leave this first one up for you to have a go at, and then I'll try and deal with the issues that people are having with the PowerPoints. If you're not watching this from Bilborough College and you want me to email you the PowerPoint because you're still working through it, my email address is andy.parker@bilborough.ac.uk. So if you're having difficulties and you're not at Bilborough College, then send me an email to this address and I will try and sort that out for you. Okay, so I've sent the PowerPoint out now. If you're still having difficulties accessing it, let me know and I'll see what I can do about it. I'm just going to go through what we're going to be doing for the next 20 minutes then. I've put 4 questions into this PowerPoint. The first 2 questions are relatively straightforward. They're similar to some of the examples I've done. Question 3 and 4 though do require a little more thought, so please do get in touch. Please email me with any questions you have about them. Ideally send me an Adobe scan so that I can look through how far you've got so far, and I'll try to get back to as many people as I can while we're doing these questions. Okay, I'll also just do a quick flick through them to show the answers in case anybody's still having difficulty loading the PowerPoint. You can then just skip through the video at any point that you need to check your answers. So this is the answer for question 1. This is question 2. Just going to display a little hint that would help you out with this one as well. Here's the answer to question 2. Here's question 3. And a hint for question 3 as well. And then the answer for question 3. And then this should say question 4, not question 5. So this is question 4. This one is quite a tricky one, so please do get in touch if you need a few pointers for it. And then the answer for question 5. Okay, so I'll give you about 20 minutes to have a go at those questions then. And I'll be here on the email if anybody needs any help. Okay guys, we've had about 15 minutes on this. I've had a few emails through of stuff that I'm going to go through. One is my first mistake of the day. I make loads of these, so please do email in as soon as you find them. We have got a little prize draw going on. Every time anybody spots a mistake, if they're the first one, then you go into a prize draw. You might win an Amazon voucher at the end of the course. So the mistake that was spotted is on question 3. If you look at the solution for part B, the answer is correct, 1.2 kilograms. So you might not have spotted it if you were just looking at the answer. However, in here, I originally had G plus 0.1, and it should be what it is now, which is G minus 0.1. So well done to the person that spotted that. Somebody else has asked me to show the answer to 4 part B that I missed last time, which is here for anybody that can't get the PowerPoint open. So I'll leave that on the screen for a few seconds. What I could really do with, before we move on though, is knowing where people are getting up to, whether you need a few more minutes to get a bit further, or if I don't want to be waiting around if everybody's done or nearly done. So I'd be really grateful if a few people could just find me an email and say, I'm up to question 2, question 4, wherever you're up to, just so I can get a feel for where people are at the moment. Okay, so I'll give people a couple more minutes. Hopefully I'll get some emails through, give us a bit of an idea how long we'll carry on with these for, or if we're ready to move on. Okay, most people are quite far along, it seems, with these questions, so I'm just going to give 2 more minutes. I'll put a timer on, and then we'll move on to the next section after those 2 minutes. Okay, moving on to the next section then, we're going to look at something called force coupling. This is a similar idea to what we were doing with pulleys in last lesson, but obviously there's no pulley going to be involved this time. So let's consider this situation first. We've got a strong man and he's pulling along a truck, probably quite slowly. There are three possible force diagrams we could draw in this situation. We could treat the man as a particle. Okay, in that case, he's got what we would call a driving force moving forward. So anything where there's a force propelling something forward, we can call that a driving force. Okay, and the reason, also working backwards against him, resisting his movement, the rope is pulling him backwards. So we'd say there's a tension in the rope pulling backwards. There may be other forces included, like air resistance. Probably wouldn't be very much in this situation because it's moving so slowly. But sometimes in these problems there are other forces as well. Okay, but in this one we'll simplify it and keep it as those two forces. Okay, I've just got an email. Let me just quickly check it. Okay, I'll deal with that one later. Right, so next up then, we could consider the forces separately that are acting on the truck. So the truck doesn't have its own driving force, it's not got its engine working or anything, but what it does have pulling it forwards is the tension in that rope that's acting backwards on the strongman. Okay, if we don't include any other resistive forces like friction or air resistance, that is the only force that is acting on the truck in this case, the tension pulling it forwards. Now the third situation, which we might want to consider, okay, it's often one of the most useful to use, is considering the man and the truck together to be just a single particle. And then what we would do is look at the forces acting externally on them. So the whole particle is being driven forward because the man is pulling it forward, so we still have that driving force. But because the tension force is acting between the two particles, which we're considering as a whole particle in this case, we can just ignore that tension force in this case. So we've just got a driving force pulling the whole particle forward. But if we were to do a force calculation here, force is mass times acceleration, we have to remember that we're looking at the combined mass of the two things. So you'd add the masses together in this case. Okay, so these problems are generally quite simple that we're going to look at if you choose the right perspective to look at the forces from. Do you use the whole system or do you use one of the particles? And that's what we're going to be looking at in the next example. So in this example we've got a truck with a mass 1200 kilograms and it's pulling along a caravan of mass 400 kilograms, and because it's attached by a rigid tow bar, they're both moving at the same velocity and consequently the same acceleration of 0.5 meters per second squared. And motion of the caravan, we're saying, is resisted by a force of 140 newtons. Perhaps that's some kind of air resistance or a combination of factors. And we've got to do two things. We've got to find the driving force produced by the engine in the truck, and we've got to find the tension in the coupling between the truck and the caravan. Okay, so the first thing we've got to decide is, do we look at the forces on the truck, the forces on the caravan, or do we look at the forces as the whole system treated as a single particle? Well, we want to find the driving force, and currently we have two things we don't know. We don't know the tension and we don't know the driving force. So because we don't know the tension, if we just go back to the example we had over here, the only time we didn't consider the tension was when we were considering the whole system here. In the other two pictures, the forces on the truck or the forces on the man, both cases there the tension was involved. So in our problem here, we are going to be looking just at the forces on the whole system in one go, because that allows us to ignore the tension. So I'll put as a diagram up so we know where we're starting from. So let's examine where everything's come from in this diagram. We've got a mass of 1,600. That is the combined mass of the truck, which was 1,200, plus the caravan, which was 400. So we've got a combined mass of 1,600. We've got a driving force pulling it forwards, and this 140 newtons, that was the resistance that was acting on the caravan. Okay, that if it's acting on the caravan, it's acting on the whole system as well. And so from here, we can just do a simple force calculation where we are resolving horizontally. soon as I've got my pen to work anyway. So we're going to resolve to the right as positive, because that's the direction of motion and the direction of acceleration. So we're going to have d minus 140. So that's forces to the right minus forces to the left equals mass times acceleration. So 1,600 times 0.5. This should be a calculation we can hopefully do in our head. We've got half of 1,600 is 800 plus the 140, that will give us 940 newtons for the driving force. Okay, in part B, just a reminder, we're trying to calculate the tension in the coupling. There's actually two ways we could do this now that we know D. The way I'm going to do it is by looking at the forces on the caravan. So, we have a tension force in the tow bar pulling it forwards. There's no driving force in the caravan. And we have a resistive force which was just acting on the caravan of 140 newtons pulling backwards. Okay, notice that both of these have the same acceleration. And so we can do another force calculation. We'll resolve to the right again. And we're going to have forces to the right, we've just got T. Forces to the left, minus 140. And in this case, the mass is 400 times 0.5. So if we add the half of 400 is 200, add the 140, we get T equals 340 newtons. Okay, so a typical thing that will happen in these types of question, if you're aiming to find some sort of driving force, you will almost always be looking at using the whole system. If you're looking at finding the tension in a coupling force between the two objects, then you're going to be looking at using one of the particles on its own. Okay, just as a point though, here where we used the caravan for part B, we could have actually used the truck, because remember we know this 940 newtons now. Once we've figured out the driving force in here, we could have a diagram for the truck where we put the driving force on going forwards. Okay. Oh, this diagram is wrong. I'm very sorry about this. That 140 should not be there because that's acting on the caravan. What we should have is a driving force going forwards and a tension force pulling backwards on it. So in this case we're going to have, resolving to the right, 940 minus T equals the mass of 1200 times 0.5. So if we rearrange this, imagine we move the T over to this side to make it positive. That the right hand side here is 600, so 940 takes 600 gives us 340 newtons again. So we could actually, once we'd figured out the driving force, we had three diagrams. We could have used either of the other two diagrams for this part of the question. Okay, so what I would like you guys to do is have a go. I'll come back to that bit in a minute. I'd like to have a go at question 1P that's on slide 60. Okay, I'll just review some of the points in the answer to this one then, some of the thought process you might go through for answering it. Finding the acceleration of the car, what you might think about to start off with is you've got, you know the driving force in this case, and you know the resisting forces. The thing that you don't know as well as the acceleration is the tension. And so if you try and work with either of the particles individually, you're going to have T and A that you don't know. So the logical thing to do for this question is to start off with the whole system. So we've got the combined mass first of all, the driving force pulling it forwards, and this 1400 newtons here came from adding together the two resistance forces of 800 and 600. Then we can form a force equation resolving to the right, and we can solve for A. I've done it to 3 significant figures. Perhaps it should have said an accuracy in the question because we weren't using G, so there was nothing to guide you for that. So if you've not done 3 sig fig, it doesn't really matter for that one. Once we know that, we're looking for the tension. You've got plenty of choices. I've done it here with the trailer. I've done the trailer, the tension pulling it forwards in the tow bar, minus just the resistive force on the trailer, don't include the other one, and that's going to equal 560 times my acceleration from part A. Something to consider when you're doing these questions: if you use the answer from a previous part in the next part, always make sure you use the exact value you've got here. It might have been that I rounded this even more, and then if I then use that answer later on, I end up with a rounding error. So try to make sure that if you get an answer from part A, store it in your calculator, use that answer for part B. Okay, I'm just going to back up a couple of slides before we move on and go through a couple of things. It's worth noticing that we've been applying Newton's third law here, which says the forces that the truck applies to the caravan will be equal in magnitude but opposite in direction to the force the caravan applies to the truck. So if we were to draw them both on the same diagram, it would look like this at the bottom here. Okay, and so the force T in each one is equal in magnitude, so we can use the same letter but opposite in direction. More specifically, when we have two forces here in between two objects, these forces are called the internal forces. And so if we're going to formalise what we've been doing in the last question, we can say that when we're working with the whole system, the internal forces will cancel out and we can ignore them. Okay, that only works provided the velocity and the acceleration of both objects is equal, but in the kind of problems we're looking at, that will always be the case. Okay, so just a quick bit of terminology there. These forces in between the particles are called internal forces, and no surprises for guessing, the forces that are not internal forces are called external forces. Okay, so I'm going to give you a few minutes now to have a practice at some questions. Questions 1 to 4, everybody should be able to have a good go at those. There's a couple of extra questions in here. I'll just review what these questions are. I'll skip through them quite quickly and give a little bit of commentary on them. I'll put the answers up as well for anybody that's still not managed to get the PowerPoint open. So here is question 1 and 2. These are pretty standard questions. Unfortunately, I haven't managed to do answers for these ones. So if you are struggling and you don't get the answers out that I've got here, please do email me. I'll try and give you some pointers, or I can annotate one of your solutions if you've had a go. So here are the answers to the first two. Okay, question 3 is a bit more unusual. It's not quite like the examples. It's the same kind of maths involved, but people quite often struggle with this problem. So if you are having difficulties, please do get in touch. But my advice would be, when you approach this problem, it's all about the diagram. If you get the diagram right for this problem and you do the 3, if you're not sure where to start, do a diagram for each part separately and do a diagram for the whole system, and you'll probably notice that one of the diagrams has got one unknown and you can kind of chain your way through the problem like that. Here's the answer to that one. Okay, question 4 extends on questions 1 and 2 in the sense that it's just a train that's got 2 parts attached to it, so it's 3 particles working together, but all of the same principles apply. You can work with things separately or you can work with the whole system, and the answers to those ones are here. And then the final few questions are past exam questions. So this was from an AQA paper, Jan 2010. Here's the answer to that one. More answer to that one. And here's question 6. Another AQA question from 2012 this time. And here's the answer to that. Okay, so I'm going to give you quite a bit of time to have a go at these. Please do email me. I'm not getting that many emails at the moment, so if you're having difficulties with anything, you're very likely to get a response if you email through about something at the moment. Okay, so I'll say maybe half an hour on these. We'll see how we're getting on after that. Okay, good luck. Off you go. Okay, I think a few people have been caught out on question 1, just by the way it's worded. So something to look out for. It says each of the car and the trailer experience a resistance of 200. So there's a resistance of 200 on the car, and there's a resistance of 200 on the trailer. So I've just done a little sketch of a diagram that I would use for part A here. The resistive force on the whole system is 400. So if you do that, that might be where the 1700 comes from. Okay, so I've had a few emails about people having difficulties with question 2. So in a minute or so, what I'm going to do is I'm going to go through a worked solution for question 2 so that we can get to these answers here. After that, I'll see what it says in my emails, and if people want me to do some of the other questions, I'll do those as well. Okay, with question 2 then, we've got a car with mass 1350 kilograms towing a trailer of mass 250 kilograms along the road. We've got the magnitude of the two forces. So let's have a look what we need to calculate in this one. We want the magnitude of the driving force first of all on the car, and state the tension in the tow bar as well. So if we want the driving force, we'll work first of all with the whole system, and we'll have a blob there that's on the floor, or floating on the floor anyway, and we'll have a driving force going forwards, and we've got 200 going backwards and 50 going backwards, so we'll say that's 250 in that direction, and we've got a mass of, well, the whole system, so that's going to be 1350 add 250 should be 1600. Okay, excuse me if I just keep pausing every now and again. I do get emails through, so I just need to have a quick read of them, see how people are getting on. Oops, sorry. Okay, we also need an acceleration for this. So if we have something I haven't underlined in the question yet, it says they're travelling at constant speed, so that means that A will equal 0. So if we resolve to the right, we're going to get D minus 250 equals, the mass is 1600, but we times it by 0, so it just equals 0 there. So we get D equals 250. Okay, next up then, you could use either particle to do the last bit, but I'm going to do the trailer. Okay, for the trailer then, scroll down a little bit. We've got a tension force pulling it forwards, we're trying to find. Remember, the acceleration is 0. We've got a mass of, well, 250 and a resistive force of 50 newtons. So 50 newtons going back that way, 250 kilogram mass. So resolving to the right gives us T minus 50 equals mass times acceleration, which is 0. So T equals 50 newtons. So that's how you'd go about doing question 2. Okay, I've got a few people asking about question 3 and question 4 as well. So I will try and get through both of those. Okay, so in question 3 then we've got a trawler raising a net full of fish. That's what's going on here. So the net full of fish has a mass 200 kilograms, and there's a little metal ball at the bottom here that has a mass of 40 kilograms. And we're told about the resistance acting on them, and we're told the tension in the cable linking the sphere and the net is 420. So with this problem, people often find it difficult to get the head around where to start. If that applies to you, then simply draw all 3 force diagrams to start off with and see what happens. Okay, so let's do this sphere at the bottom here. Okay, we've got a blob. We know the sphere has a mass of 40 kilograms. We'll pop that at the side. Okay, we don't know what the acceleration is. I'm going to assume that it's upwards. If that's not true, it'll just turn out that A will end up being negative if I calculate it. Okay, and there is there's a tension force pulling this up. We'll cut, because there are two tension forces here. We know one of. Hang on, sorry, I'm mumbling. We know this tension because it says the tension in the cable linking the sphere to the net is 420. So this force here is 420 newtons. The water resists the vertical movement of the net and the sphere with 120 and 20. So on the sphere, we have got 20 newtons coming down here. However, the bit that people often miss is that just because this particle is underwater doesn't mean that the force of gravity doesn't act on it. So it will still have a weight. So it's also going to have a force downwards of 40g. Doesn't matter that it's in water, that force will still be there. Okay, so here are our 3 forces. The other point to mention is why is this 20 newtons downwards here? Well, if this particle here is being pulled upwards and it has a resistive force, then that resistive force must be in the opposite direction. So that's why the 20 newtons is going downwards. So looking at this, straight away, even though we haven't drawn the other 2, we can see that we only actually have one unknown in this problem. It's not the thing we're actually asked to calculate, but we could do some calculations with this anyway. But we'll draw the other diagrams as well, and then we'll come back to calculating A if that's what we need to do. So we could then do the whole system. Okay, so treat the whole system as a single particle. It's going to have a total mass of 240 kilograms. And this will also have the same acceleration A, going upwards. Now remember that we've got this tension in the cable linking the sphere to the net. The sphere is below it, is 420 newtons. Remember Newton's third law, if it's pulling upwards on the sphere with 420 newtons, it's pulling downwards on this. Oh, hang on. Ignore what I'm saying there, because I thought I was getting messed up and doing just the net there. I'm working on the whole system. That means the tension in between the 2, we'll ignore it because it's acting upwards with 420 on that one and downwards with 420 on the net. So we've got this tension pulling upwards here. That's ultimately the thing we're trying to calculate, the tension pulling the thing up. Okay, acting downwards then, here we've got a weight of 240 g. Just give me a second while I look at my email. Okay, back to this then. But that's not the only force, because remember we've got these 2 resistive forces here as well. So that's a total of 140 newtons. So we've got 240g plus 140. Notice in this diagram though we've got 2 unknowns. We've got T and A. Okay, I'll just draw the one for the net as well. I don't think we're going to end up using this one though. So here's the net. Okay, the net has a mass of 200 kilograms because it's got a load of fish in it. Okay, the net has a tension pulling it upwards. Same tension as we've got in here. It has a weight of 200g. And we also have a resistance force that's acting on the net, which is, oh god, didn't mean to do that, is 120 newtons, so plus 120. What we don't have is the extra 20 in here. Okay, so looking at this diagram, we have the same issue as with the whole system. We don't know T and we don't know A. So you could actually work with either of those there. To start with though, I need to work with the sphere. I'll resolve vertically upwards to start with. I'm going to get 420 upwards minus 20 minus 40g. So that's forces up minus 40 down, and that equals mass times acceleration, so 40a. Okay, I'm mindful that we're running out of time here, so I'm not going to finish the whole question. I will come back and I know that some people might want to finish at 3 o'clock, and I want to get through all the questions that people have asked me to. I will come back after I've finished the other questions and complete the working out, but I will just give you the rest of the method for doing this. If I divide through by 40, I'm going to get a for that, and I could just write down a equals whatever it is. I don't know, I haven't got the answers to this without working it out. Once we've got that, we could then work with the whole system. We could do a force calculation for this one. So if we resolve upwards, we're going to get T minus 240g minus 140. So that's the net force in this, and that's going to equal mass times acceleration. So that will be 240 times whatever we got for that part, and then you can rearrange that and solve for T. Okay, so at the end I'll come back and I'll try and fill in the gaps for here just to make sure we've got the right answer out. But in the time being, I've got quite a few people asking about question 4, so I'm going to have a bash at that one as well. Okay, question 4 then. So in this one, this is the one where we've got a locomotive pulling 2 carriages along. And we want to, first of all, figure out whether it's driving or braking. So is it a driving force or is it a braking force being applied to it? And then we're going to look at the coupling forces in each one, and we'll talk about what tension and thrust means in those circumstances. So we've got loads of information in this question, but the key thing we need to spot, if we're trying to figure out a driving or a braking force, it's the same thing, it's just whether it's accelerating or decelerating. That means we're going to be ignoring the tension forces, the coupling forces in between or maybe their thrusts, we'll find out later. Which means we need to work with the whole system to start off with. So this is my train, it looks like a circle for some reason. We're going to start with, we'll assume it's a driving force in that direction. What will happen if we end up with a positive answer for this? That means it's pulling it forwards, it's a driving force. If it turns out D is negative, it really means the arrow should have been drawn in the other direction, in which case it's a braking force. It's decelerating, so the acceleration is in the opposite direction, and that's 2 meters per second squared. Okay, so let's have a look. What resistive forces do we have working on the whole system? We've got 9,000, we've got 6,000, and we've got 3,000. I believe that equals 18,000. Working backwards like that. And we have a total mass of 400 for the locomotive plus 2 lots of 2,000. Sorry, 4,000 plus 2 lots of 2,000 should be 8,000 kilograms. So, resolving to the right, we are going to get, just 1 second, D minus 18,000 equals 8,000, the mass, times the acceleration, which is Oh, be careful here. I've chosen right as a positive direction. That was maybe a little bit silly in this case. On this side, I'm going to get 8,000 times -2 because the acceleration is to the left. So I've got -1600, but then when I move the 18,000 over to the... sorry, I've got -16,000 here. When I move the 18,000 over to the other side, that will give me +2,000. I'll put a plus there just to be clear. No, I won't because it looks weird. I'm just going to put 2,000 newtons. So because this value is positive and I put it as an arrow going forward, that means that's a driving force. Okay, next up in part B, we want to find the coupling force in each of the two carriages. Okay, now the order I do these in will matter. First of all, if I start with the back carriage, okay, so this is carriage number 2. It's being pulled forward, we'll say with a force, we'll call this one, this is the second carriage, so we'll call it T2 in there. There's a resistance force on the back carriage, which is 3,000 newtons. We've got an acceleration to the left of 2, like so. Okay, these are the only forces acting on the second carriage. The reason I've chosen this one first is because if you imagine, I'm not going to draw it yet, but if you imagine the middle carriage, we don't know this tension force, which will be on the left hand side of that carriage, and we don't know the other tension force on the other side either, so we'd have two unknowns and we wouldn't be able to go anywhere with it. Okay, we could actually work with the locomotive to find the other tension force, so that would have been one possibility as well. That's just as equally as acceptable. Okay, working with this then, just to be consistent with what I did here, I'm going to resolve to the right as positive again, which means I've got negative acceleration. I've got T2 minus 3,000 is going to equal the mass of this one, which I haven't written down yet, is 2,000 kilograms. So 2,000 times -2. Okay, so what we've got here is -4,000, but then plus 3,000, so T2 will be -1,000. Okay, so actually, rather than, if I just draw all three carriages somewhere, maybe over here. Okay, what you normally have when a train is going forwards is the locomotive will pull the middle carriage, which will then pull the end carriage. But we've got a different situation here where it's decelerating, and what's happening, because this T2 force is negative, it's actually not in this direction, it's pushing back in the other direction. Okay, so what we find is that actually, rather than this one being pulled along by that force, because of the braking that's well, not the braking, because of the deceleration that's happening, it's actually being pushed backwards. So rather than a tension, this one is a thrust. Okay, and it's actually acting backwards. So now, part C, just a second while I read my emails a minute. Okay, part C then, we'll draw the middle carriage this time, and we'll have a think about the forces acting on that. It's going to have a tension force pulling it forward from the locomotive. Well, maybe it will, maybe it'll be another thrust force. And in this case, we need to think a bit more carefully about what's going on here. Because what was acting on this force, this diagram is actually not quite right. This T2 force is acting backwards there. And so, because we've got an equal and opposite force, what's happening really is this carriage here is pushing this carriage forwards. So we would actually, I won't draw it here because this would be an incorrect force diagram, but T2 is really pushing that one forwards, and that's what we found out in part B. So really what we have is T1 plus T2, which is 1,000. Okay. Mass of this one is hang on. I'll write my 2 meters per second my acceleration there. The mass of this one is also 2,000 kilograms. Okay, let's do a force calculation for this one. We would have T1 plus 1,000 equals the mass of 2,000. The acceleration is in the opposite direction again, so minus 2. Hang on, I've just got another email through. Okay, back to this question then. Oh, hang on a minute. I think I've missed something off on this diagram. I've forgotten the 6,000 Newton resistance force, so let me just pop that on there. Okay, so I'm going to have to do a bit of a correction on this. Sorry if you wrote it down while I was writing it down. We do still have T1 plus 1,000, but we need to have a minus 6,000 on there as well. And that equals 2,000 times negative 2. So we're going to have negative 4,000 plus 6,000 gets us up to 2,000. Take away the 1,000 gives us T equals 1,000 newtons. Okay, now for this one then, because we got a positive answer, it means we got the T1 in the right direction. So this is pulling that one forward. So this would be a tension force. Okay, so there's an interesting thing that arose in part B that's worth being aware of. Sometimes you put an arrow on a diagram because you don't know which direction a force is. But it doesn't really matter, because if it turns out that you chose the wrong direction, you just get a negative answer, and all that's telling you is that force is really in the opposite direction. Okay, so that's all of question 4. Okay, a couple of people have asked for question 5 as well, so I'll stay here and I'll finish that. For anybody who's done though, thanks for watching, and hopefully we'll see you in the next lecture. Okay, I'll start this one in a couple of minutes. I've just got a couple of emails to reply to first. Okay, let's. The only one I've actually been asked about for this one is question 5C. So I'm just going to have a quick read and see if we can do it without doing the other parts. I'm not sure we'll need to. No, I think we might be able to just get away with doing 5 part C. Hopefully I won't just fall flat on my face by saying that, because quite often if you don't do an earlier part of a question, you end up making a mess of it, but we'll have a bash. So we're going to find the magnitude of the force that the rod attaches to the rod attached to the engine exerts on carriage 1. So that's this rod in here. Notice that in part B we found out the force that the rod exerts on carriage 2 is 550, so we know this force in here is 550 newtons. So let's see if we can draw a little bit of diagram for carriage 1. So we have got a blob here. We've got 550 newtons. Let's just make sure we get the right direction for this. Okay, so I believe we are going to have a 550 Newton force here. Okay, the one we're trying to find is this one here. We'll call that T. Okay, each carriage has a mass of 500 kilograms, and the whole thing is accelerating at 0.5 meters per second. Let's just check that's all of the information and we haven't missed anything. Yes, we have missed something. We've got a resistance force of 300 newtons acting on each of the carriages. So we need to have 300 plus 550 newtons in here. Oops, sorry. Where's my page gone? So, no, another email. Okay, let's finish this one off then. So, resolving to the right, we will get T minus 550 minus 300. So that's the net force. Equals mass times acceleration, so 500 times 0.5. Hopefully this is one we can do in our head. That's going to give us 250 on this side. That's going to give us minus 850 on this side. So when we add that over, we should get 1,100 newtons. Okay, let's just have a quick check. Is that the correct answer? Yes, it is. So we'll just pop that back up for a second. So here's the answer to question 5 part C. Okay, that's it for today's lecture. I have got a couple of emails that I'm going to finish replying to, so if anybody sends anything through in the next couple of minutes I might be able to have a look at that. But thank you for watching and stay safe.